All right, I think that means we're live. Good to see everybody again. Today we have Steven and Aaron like usual. We have Ron as well. So Ron is an engineer on the storage team here. We'll dive into his work later with some contributions to the Firewood effort. But yeah, first we'll get things started with Cortina 11. So let me present my screen here. Too many tabs. There we go. Cool. All right, Steven, take us away.
Yeah, so for Cortina 11, the namesake of the release is really the major thing that I think we want to talk about, which is the archive DB. So traditionally, for APIs or like blockchains, as time goes on, the database grows significantly, very large amount. So if you're running an archival node, you'll notice your database is many multi-terabytes. And one of the big reasons why the database grows so much is because of storing all of the historical Merkle tree structure, which is actually the backing structure that I think we'll talk about a lot more with Firewood, but that is used to kind of like keep track of the values of the state as time progresses. In order to serve API queries, you don't actually have to have any of the intermediate Merkle nodes. You really just need to have the historical values. And so there have been a number of different kind of ideas around this area about how you can more efficiently store historical state at given heights. And so this is kind of pioneered by some of the Ethereum teams with like Aragon and now Reth and things like that. And so this is a very kind of corollary implementation that's going to tie in well with the Merkle DB, which is basically a high performance database for storing the current Merkle tree state, so the current state of the blockchain. And then the archival DB will be able to efficiently store the historical values of the state of the chain. And so this should be able to, manage to have the much smaller disk sizes and much faster disk lookups for historical state that you see in like other more advanced database structures like Aragon and Reth. So this is kind of the big first pass on it. It's not too much code. It's pretty simple right now. This is more or less a prototype to just kind of understand the database schema that we'll be using. So I think a lot of the future work here is going to be playing around with different database types. This is still backed by LevelDB typically, or just the generic database interface, but we'll probably be playing around with different database backends to further kind of optimize this. Yeah. But yeah, I think
at Avalabs, like databases are a dime a dozen here. We're cranking out a new database every week, at least at this point. No, so this archive DB is actually, I think, a really interesting way to structure this. So as like an entirely separate, really versioned value store. So it assumes nothing about the tri structure whatsoever. So you could just use any tri structure with this, like whether that be the EVM, whether that be Merkle DB, whether that be some other tri structure, and then takes advantage of actually the opposite of what a lot of other stuff we're trying to take advantage of is, which is database iteration. So a lot of the databases that are currently used, like for the embedded storage area, just by their design include iteration, basically saying that for any arbitrary prefix, you can iterate in order. Sometimes they allow you to also iterate in opposite order over like the range of full keys. And so instead of typically saying like, hey, like I know the key, just give me the value there, you may also want to say like, I know part of the key, give me like the next value. And to power this efficiently, you often hear this phrase like the database needs to be like compacting things or like has to take extra time to like put things in a certain place so that I can do this efficiently. In some databases, it's actually not desired to have or required to have things in sorted order. But for this particular database, it's very much required. And I think it makes sense for us to dive into some of the way that the keys are structured to allow for this, or like what we're actually doing here, which is to say, basically what this database is trying to solve is, I'm saying I updated the key, some key to like, in this example, like I'm setting the key foo to like foo's values bar at a particular height 10. Now, let's say I'm at height 15 and I want to know the last value of foo efficiently. That's what this database is trying to provide. And you can imagine that like if you're trying to like provide historical execution or like historical data, like maybe a balance instead of foo at a particular height, that you don't want to like have to store every key at every possible height. You just want to store it at the last time it was updated and then be able to efficiently fetch that last value. So I'll switch over to the key side. And this is very similar to some of the stuff that Aragon kind of started to work with. It's also similar to the way that balances are tracked in the Rosetta CLI, if you're familiar with that tool. Let's see where the keys are.
The key structure is also going to change ever so slightly in the next release, so 1.10.12. But yeah, essentially the invariants that are at play with the keys is kind of the major point, and then how you actually maintain those invariants is almost kind of a detail. But essentially what you need to do is you need to make sure that for a given key, that maps into a specific prefix in the database that is isolated to that exact key. So, in the foo example, if you had like foo with like a bunch of O's tacked onto the end, natively foo is a prefix of that foo, FOOO, which means that they kind of have this kind of like corrupted prefix or like corrupted namespaces issue. So in order to get around that, we essentially prefix that key with its length as a uint or like as like a variant encoded thing. And so then that variant length concatenated with the key is essentially the prefix that is used for that that key. And then if you want to have different versions of that value, you tack the height on to the end of it. So the actual key format ends up being the length of the key, the actual key, and then the height at which it was modified. And then the value is either that it was deleted at that time or that it was modified to some other value. And so this lets you have your concrete namespace for each key, and then you can efficiently iterate over that namespace to find the most recent value for that key given a given height. So that's kind of I don't know if that's the intuition or if that's actually the down and dirty details of how it works, but that's kind of the insight here. Currently in 1.10.11, we prefix with an additional 0 to give us a metadata namespace. But in 1.10.12, we'll do a little bit of a slightly more interesting mechanism so that we can reduce the key sizes by that 1 byte while still giving a unique namespace to metadata keys. Currently, the only metadata that we store is the most recent height that was written, and we do that just to provide more like atomic guarantees around what was written. So if you're like writing to multiple databases and then you shut off, you need to have some way of recovering, and so it's very useful to have that knowledge in the ArchiveDB. But if we add any more metadata keys, then we have that namespace to use that. So
yeah. And then I think people, just to iterate or to explain what this is for, so this will be used most likely in the HyperSDK as well as the EVM, as well as really anyone that wants to add archival like lookup support to one of the virtual machines on Avalanche, and should reduce like the storage size of otherwise storing all the intermediate nodes in the past by, I think usually people see like a 70% reduction in storage use or storage space, or 80% based on what their workload is. And just to be transparent about like, well, there are trade-offs here. There is one particular trade-off, which is that because we no longer have the intermediate nodes at historical points in time, we cannot generate proofs quickly of historical data. So you're asking, like, well, why doesn't everyone do this? Well, if you want old proofs, like you're not going to be able to get that with this mechanism. But I think what we've seen in practice is that most people, when they're querying, just get want to get the values at that historical height rather than particular proof of some value there. Yeah, to do that, you'd have to do some probably like rewind process or something crazy. I'm not even sure.
Yeah, I think honestly, if you're trying to serve the proofs, then the existing kind of like hash-based Merkle tree approach is pretty reasonable, and that's just kind of the cost overhead that you have to deal with. But yeah,
I think archive. Yeah, the main point there.
Yeah, there's a bunch of other like small updates and tweaks and things like that, kind of pushing to prep for the next network upgrade. But
yeah, I think there was like a small regression in like how we were handling app requests for people that hadn't updated to 1.10.11 yet, which introduced, or 1.10.10 yet, which introduced pull gossip. So that was also relaxed. So now if you don't respond to something in that vein, it doesn't like bench you. Instead, what it'll do is just in the future, what you'll respond with like an app drop if you can't support a particular like P request protocol. Cool. Yeah. So next release, I think, is on track for tomorrow. You can see all the updates coming with that one. There's a ton of MerkleDB changes that are coming, which is going to be pretty cool. I know Steven's particularly excited about the branching factor change, which will allow you to set an arbitrary branching factor for the I guess, is it a power of 2 branching factor?
Yeah, so you can either do a binary tree or a branching factor of 4, 16, or 256. So it has to kind of fit into a byte when broken apart.
So that'll allow for some different trade-offs. That was something that we were working on with like if people remember like the light VM stuff with like how we would actually generate these proofs, and that because we had required like 16 there, that like the proof size was larger than we'd like, especially because the proofs were like included in some of the blocks. And so if we can minimize that, it makes something like that much more palatable, I guess, from a network efficiency perspective. Cool. All right, so the next one we will go into is Firewood. So let me pull up that one here. Let me just preface this with a few things. So Firewood. I apologize for not having this up. All right, so I'm going to preface this with a few things, and then we'll turn it into kind of a group conversation on this topic. So last week, I think on Wednesday it was, we opened Firewood up to the world underneath 2 different licenses. So there's one Firewood repo, which is just Avalabs/Firewood. Which is under the ecosystem license that we've been using for a number of different projects we've been working on, and then a separate one under the MIT license. So for those that aren't familiar, Ted Yin, who collaborated, or really was the one that actually built the initial prototype of Firewood, originally geared that for the EVM, and the original prototype was that. And so the Firewood-MIT repository, which I'll share here, includes everything focused primarily for like EVM and EVM tri-E compatibility. Since the original prototype, a number of folks other folks at Avalabs have been using and extending Firewood for compatibility with the MerkleDB tri-E format. And so Ron, who's on the call here, has been one of the contributors to that effort and getting things compatible with our MerkleDB implementation that we're switching our virtual machines over to. But I wanted to just highlight really the important here that Ted was the original implementer of much of the Ted was the original implementer of the prototype for Firewood, and had a lot of the insights into how Firewood would be laid out. And then, our implementation paths diverged, and the Firewood that is currently at Avalab/Firewood focuses on MerkleDB tri-E format compatibility, and will be something that we're working on kind of evolving to fit into everything. So first off, we'll turn it over to Ron to introduce himself, and then we can talk a little bit about what Firewood does differently than other traditional databases.
Yeah, cool. Hey, I just wanted to also just add to what you said. Look, Ted did a fantastic job in making a prototype and expressing his ideas. He had this idea of how Firewood should work, and it's a novel idea. It's super powerful. And what he did is he just said, I've got this great idea, and he just wrote a bunch of Rust code, in a prototype way. And it was awesome. The end result, architecturally speaking, uses a lot of really cool ideas. I've only been at Ava Labs for like 8 months now, and that's mostly been what I've been working on. But the ideas behind Firewood, it solves a lot of problems. One are like performance bottlenecks in the storage layer, being able to read things very quickly for the current or very recent versions, easily reaping older data. There's no like collection process or garbage collection that needs to happen. It's got this really powerful version caching system kind of built in to the way it's architected. So it's got all these great ideas. These aren't like totally new concepts, but putting them together in a brand new way, right? So if you're familiar with traditional databases, there's this thing called snapshot isolation, where you can look at like a particular version of a database. Well, that's exactly kind of what's implemented here. It's the same implementation that I've seen in other databases to layer different versions of things and be able to see things very quickly. But it also has some concepts that are taken from things like overlay FS or union FS or ZFS, where you can kind of make writes to something and kind of have them sort of appear in new versions, but be able to see older versions too. So the concepts are really cool. That combined with a write-ahead log that you also see in many databases, it's just kind of a new thing. It's a new idea. My background is mostly in database theory. So I worked on file systems, transaction management, performance work, and also in Rust. And so I'm happy to say that, Rust is a great prototyping language, and Ted was able to get his ideas expressed relatively easily in Rust. We've just gone back and started to make enhancements to it and just kind of applying our opinions of how things should be laid out.
Yeah, I think as we've worked on MerkleDB, our ideas around what a blockchain database should have for our use has evolved quite a bit. And so I think the big thing you'll notice is the primary aspects of Firewood are really efficient mapping of state to disk, which is without compaction, kind of using the actual tri-E structure as the index on disk. But there's this important part that's ahead and an important part that's behind that we now utilize heavily. So on the proposal side, right, when you were actually verifying blocks that are not yet committed, tracking proposed changes effectively is really important, because you have to still potentially generate routes or generate things for things that are not yet confirmed or on disk yet. And then additionally, Firewood now supports or is close to supporting state sync, so that we can allow people to sync off of Firewood. But if you just store the state on disk for people to sync off of, it becomes actually really difficult to use in practice, right? Because the blocks are actually changing very quickly. So by the time you request a state proof or a range of values in a state proof, you may not the node you're asking may say oh, well, that was last block, I have no idea what you're talking about anymore. So there's now a set diff limit that's kept in memory to still service state proofs and change proofs over an abbreviated history, which is really important in practice for actually letting people synchronize state off of nodes that are actually running Firewood. And then the last thing I wanted to touch on that's really important is when we were originally starting Firewood, when we were kind of planning out maybe this sort of thing could exist on Avalanche, how would we actually implement it or actually integrate it into the network? We also didn't have as clear of ideas of what would make sense. And so we've now come to the conclusion, though, that we're trying to standardize the tri-E format across the different virtual machines that Avalabs manages. And so this single tri-E format is compatible with drop-in replacements that implement this MerkleDB format. So if you implement like support the MerkleDB, you should be able to just drop in Firewood without any particular change. Like basically, it wouldn't require a regenesis because the trie structure will stay the same. And we're hoping that the state sync and change proof format is also going to be directly compatible. So you can just use that, use something else, or like as we continue to innovate on the state management layer, that like you will just be able to continually drop in different things. So this is like unique, our own trie structure. And we think that it, services our use case at least particularly well. I know, Steven, you were going to mention something there.
I was actually going to ask Ron a question. I think the historical diffs are actually stored on disk for Firewood, right? They're in memory in MerkleDB, but
so it depends on how you want to look at them. So there's this thing called a write-ahead log, and that write-ahead log does keep on disk the historical data, and it's primarily used for during recovery. So like if the system were to go down, you don't have that in-memory trie is not sitting in memory anymore. So you have to reconstruct it at startup by reading the write-ahead log and kind of going back in time and figuring out what things used to look like. But that kind of gives you a way to like restart the system without having to, like worry about the fact that there's no history, right? But we only store on disk the current trie and the actual batches of what's changed in the write-ahead log.
Cool. Sick.
Yeah, so the other thing that we're doing, we're making a bunch of architectural changes, and we're in the process of doing that. Patrick mentioned a few of them. We really want to get state sync up and running and be as compatible as possible with the MerkleDB trie format. We kind of want to be able to plug in any kind of node storage because we think that being able to store nodes in a different way would be cool. Long term, maybe Verkle trees or who knows what we'll come up with as a node storage. We want to be able to plug that in at the end. But we also want to, we really want to get everything to be async. Rust has a really powerful async support system. We want to change the IO subsystem to use, the more current and pluggable IO subsystems. And so there's a little bit of work that we're needing to do there to try to get the performance to really shine here. And then we're going to look into like better caching strategies too, to preload some nodes maybe needed for root generation or whatnot. We'll be able to identify what those areas are after we get all of the benchmarking done, which is really our main focus right now. We want to just compare it against MerkleDB and see where we are. So we should be able to, we're actually actively working on that right now. We should be able to get something pretty shortly.
Yeah, that was the first question we got was like, cool, looks really cool. Like, looks like it should be fast, but like how fast? And, our response to that was, well, we're almost there to say with confidence, like where the performance threshold is. But it was important to us, to get the ideas out there of like the major things that were being worked on so that people in the community that wanted to contribute to it, wherever they are in the Avalanche ecosystem could do so for their own use on virtual machines and such, because any virtual machine that's running on Avalanche can just use this database however they see fit. I think the funny note on that as well is like the MerkleDB group is not just like standing still, so a lot of changes coming there that are, very optimization focused. So, we'll see what kind of competition, we have here to see what sort of throughput you guys can put together. But as a result of this, and because everything is so compatible, we're building a single benchmarking suite that will allow any basically database that's compatible with this trie format just to plug into it and then get load tested in the exact same way. So the important part of like any performance analysis, and something that's also important in the HyperSDK world, is the ability to have these like reproducible and comparable benchmarks. And so in this case, we are going to have exactly reproducible and comparable benchmarks of the same trie format in different mechanisms. Not only that, but also in different languages, which would be kind of cool to see how like memory efficient it is, disk efficient it is to handle certain workloads. I mean, we're particularly excited about this. I think we have at least three or four folks internally working on this full time, and all out in the open now. So you can follow along on the GitHub at on Avalabs' organization. Yeah.
We're going to win, Patrick, because we're not going to do any memory allocations during inserts and stuff. So we're going to win.
You You should see all the random unsafe string slice stuff that David has been working on to reduce that on the Golang side as well. But yeah,
we'll have to
Firewood
have a little
should win.
tool. Yeah. Yeah, it's more of a reflection on you if it's not faster. So but yeah, we I think like how we utilize this with different sort of like tools that are available is going to be really interesting. Like I think one of the things that was talked about is, even if I think this is one really important point to bring up, which like even if things are stored super efficiently on disk, the actual like execution against or like modifications to a Merkle tree, like there's a lot more to it than just the disk aspect of it, right? So like if you, let's say, are trying to generate a new root and you have to modify like a bunch of sort of intermediate nodes, if your expectation is that you have to, like, maybe they're stored efficiently, but you now have to read like a bunch of different nodes off of disk, that doesn't mean that it's going to be faster, right? Especially if all that's stored in memory. So like having like really efficient look ahead and knowledge of like the data structure is actually being used here can make a huge difference. But the idea that like just storing exactly the structure on disk will have huge benefits to like efficiency, as well as I think the opposite of what we talked about earlier with the archive DB, in that there's no need to compact everything, because compaction is really a function of this like LSM based tray structure that like a database typically use, and that's used to keep things in order. But if everything on disk is in like already a tray structure, you never actually have to like reorder things in logical disk space, which can lead to a lot of benefits. Some folks actually, which is interesting, I wanted to give a shout out as well to like the Aptos research group, implemented this thing called a jellyfish tray, which inserts key, basically has keys that are prefixed by the height that they were modified at, so that when you use an LSM database, it doesn't trigger like a bunch of compactions on disk, which is, I think, a really interesting approach to trying to resolve this issue, which is to say, we'll just use the still best in breed LSM database like RocksDB, but we'll just insert things in a way that is more compatible with its performance. Or like will help it perform better, rather than saying like we're going to redo how the entire on disk index works. So this is a very different approach to solving that problem, and this one is more suited just for the current state, which I think is interesting. So it's going to be much better for like deletions and such, which in the Aptos case in that jellyfish database, like deleting old key values is not. You still are now going to create gaps in the database and require like historical compaction. So if you want a archival database, it works really well. But if you want like a really only latest state database, it still doesn't have the efficiency on disk, at least of this process.
Yeah, just kind of outlining that. If you look at the architectural diagram on the screen, if you look at the B2 layer that's at the bottom, that's the oldest version that's visible on the screen. Obviously, there'll be more than just two versions prior to the current one, but that would have made this slide really hard to read. So there's only like two shown. But if you wanted to drop B2, all you need to do is free up the memory that's in that light purple or whatever color that thing is, light pink colored line at the bottom there, and you're done. I mean, it's just a couple of memory frees. You're just basically freeing those 3 blocks and everything is done. So compaction or garbage collection is just a memory free of a few pointers. It's really kind of cool.
Yeah. So if you want to learn more about this, we, Ron and I collabed on this article talking about, why you'd want to build something like this, how it all fits in. But it's definitely, it's been something we've been working on for a long time, and something that we'll continue to work on for a long time. So if you're curious to get started, now's a great time to hop in and contribute. I think we've already had a few new external contributors pop up, which is fun. And definitely inspiration for me to finally learn Rust, this and the HyperSDK programs in general. For people that know me, I'm very much in the Golang world, not yet in the Rust world. So, excited to finally dip my toes in there. And Rust, Ron and I have talked about, the first time I met Ron, we talked about Rust for about 2 hours in a coffee shop before we talked about anything else. So that should tell you everything you need to know about Ron.
Yeah, I'm a big fan.
Right.
I think it's a great language.
Cool. Aaron, anything you want to add here, Aaron or Steven? on top of what's already been said? Otherwise, we can move on to the next topic. All right, cool. So the next one is something that Steven has been working on for some time now. And if you're looking for an example of what a perfect PR description looks like, look no further than PR 2125 in AvalancheGo, which has the most I've ever seen Steven write. So that should, but Steven, I'll turn it over to you.
Yeah, so I use this opportunity to actually fix the specification of Snowball because the paper has been a little bit out of date, and I've been really bad with updating as tweaks are made. So this includes both the current reference implementation of Snowball and also kind of these proposed modifications. So we've been working on Avalanche consensus for a while now at Ava Labs, and we kind of had this insight that there's some improvements to be made on how nodes are actually like kind of selecting and adopting their colors. So the current parameterization of Snowball has a bunch of parameters, but the key ones is the number of nodes in the network, the sample size, which is K, alpha, which is essentially the quorum size, and then beta, which is the number of consecutive rounds required in order to terminate. And those are the kind of the four major values. In practice, increasing the alpha and decreasing the alpha does two things. So increasing the alpha can increase security. You're requiring that the network is more heavily decided one way in order to actually finalize that value, which means it can tolerate more Byzantine nodes reverting and still being a majority or supermajority of the network. But increasing the alpha also slows down how quickly the nodes can adopt a new preference, especially if the network is 50-50 split. So this description has a number of simulations where we play with alpha in two different kind of network modes, both lockstep and sampled. And we can see that the rounds until termination as alpha increases grows a lot. So in this case, K is 21, which is very similar to the existing mainnet parameterization of 20. And as alpha goes from like 11 to 16, we can see this kind of like growth of the number of rounds required really increasing. The reason I cut it off at 16 was because past 16, it grows really rapidly. So if you keep running the simulations, like I think this stops at 19, but if you go to like 20, it's like tens of thousands of rounds, and like 21, I gave up because it was taking too long. But presumably it would finish, but it takes a long time. And similarly, so I ran this for both like different network simulations where you run the network in lockstep or with sampling, and it doesn't really matter too much for the existing case. So here we can see a very similar pattern. So if we scroll down again to the next graph, we see it continue to blow up a lot. And so the kind of key thing here to notice is that we have two mechanisms. The first mechanism is picking the color, and then the second mechanism is the finalization detector. And this PR is just very explicitly separating them. So the finalization detector is the thing that actually provides security. So making sure that the network is not going to revert back. And the first mechanism, we kind of just piggybacked on the finalization detector. Or it was kind of like really the other way around, but you need to increase the alpha in order to have reasonable security. So what this does is this fully separates those two mechanisms out by having two different alphas. So you have the alpha preference and the alpha confidence, which is a very minimal change to the reference spec. So we can see here, it just basically adds 3 lines of code. But what this means is that you can parameterize it so that you very quickly adopt a color early on, even in a 50-50 split. But you still only terminate once you have that very high confidence that the network doesn't revert. So you still kind of keep that security, but you're much more willing to switch your color if you're kind of undecided in like a 50-50 split. So we can see with the below simulations from here that the number of rounds until termination do still grow as alpha increases, but they don't kind of have that. I don't really like saying exponential because I haven't actually done the math out to like see what it grows as, but it kind of seems like it grows exponentially as k gets towards as alpha gets towards k. But in this case, that's very much not the case. It still grows, but it grows at a much more kind of reasonable rate. And so this is a very, I think, and practical, and I think the simulations show that this is a very practical way of keeping the performance very high without negatively impacting the safety. So one cool thing as well with this PR is that if you keep alpha preference exactly the same as alpha confidence, which is essentially the exact same protocol that we have right now. So this PR actually doesn't change any behavior of the node. It just adds another degree of freedom that we can tune the consensus for. And so I think that we'll probably be merging this PR in pretty soon. But the later kind of work here is going to be what we actually set these values to, which is going to be kind of blocked on a more in-depth safety analysis because this does have some safety implications, but based on some very rough simulations, it should basically just be the variance of the sampling rather than the actual like percentage of Byzantine nodes, which as k increases, it's not incredibly significant. So yeah.
And yeah, I mean, I think the intuition here is to say, if you're trying to get a sample to be successful, so like in a successful sample here means that like alpha divided by k or greater of the responses are for a single color. Obviously, like the probability of success there goes up the lower alpha is, but the trade-off, as Steven mentioned, is that the security can go down, right? Because like if you only require like your samples to have half of a preference, like obviously that in repeat samples means that like the coloring of the network is much less decided. And so if you decide too soon, where that people may still revert, then you can tolerate a much smaller adversary. And so the idea is there some way that we can separate the preference detector from like the preference mechanism from the finality mechanism that will allow us to hit the tipping point of getting away from like a colored split much more quickly? Now, in practice, we typically don't see this colored split much because of the Snowman++ like soft leadering. But in the case where there is maybe network stability because of some data center issue or whatever like that, we may see more rejected blocks. And in a world where you have like more competing proposals, this mechanism can ensure that the network continues to stay healthy at that time.
Yeah. I think that there's probably going to be a lot more work into this area of kind of like splitting up these preference selection and finalization mechanisms. So like as we split this out, I think we can kind of continue to perhaps modify both of those separately. But as is, this PR basically aims to make as minimal of a change as possible while also explicitly delineating those two mechanisms. So
yeah, I think as like we were working on some of like the safety analysis of like how this can like what parameterization to pick, the interesting byproduct of that is if we are able to come with like a more efficient or like closed form mechanism for determining the trade-off of a particular parameterization, we could even allow maybe like having like a softer preference view of state. So right now, AvalancheGo only exposes accepted state according to your node. So like if you want to query some value, you wait for full acceptance before you can query it. Now, this is very different than almost every other network. So like Ethereum, for example, exposes the processing state, like L2s expose like the soft confirmation state. Solana does something in the middle where like they expose like this kind of like soft confirmation point, which is like works as long as there's less than a certain percent of Byzantine preference. And Avalanche could be adapted to do a similar thing, which is to say, okay, if you choose a particular safety parameterization, let's say you're willing to trust that preference tip as long as the Byzantine adversary is under 5%, you may be able to query the particular data that's needed, maybe when it's completed X beta in a row rather than the full beta in a row, and allow the node to behave in that way via separate endpoints or something like that. Not going to be fun to implement those changes, but at least from a TX confirmation perspective, it definitely may make things feel much snappier. And people can utilize that sort of confirmation in their UI if they are okay with reversions at some probability basis of like a Byzantine adversary. Right now, we don't have that, so we could just expose like processing tip. But I don't think that's a very, it can move around a bit at different times, and we haven't really communicated much around it, like the stability of that preference. So I think that's some other interesting research of this along this vein we may go into. Yeah. Also with playing with the trade-off of like, if we make K bigger, can we reduce the rounds? Or like in the world where like there already is a lot of preference to a particular color, can we more quickly just confirm it if we believe that the network is pretty well colored already? So yeah, we're working on it with a number of different research partners on this topic. So hopefully we'll have some more research to go out with this relatively soon. So yeah, anything else you want to add on this one, Stephen?
Just the real quick last comment. The reason that the last graph shows an increase versus the last graph is showing basically the modified version with alpha preferences 11 with sampling the nodes. The actual reason why you see that growth, whereas in the lockstep it's linear, and I commented this I think in a follow-up comment below, but I think it's interesting to shout out, is because the sample, you might end up sampling kind of like not the wrong node, but like sampling the node that hasn't yet changed its color, which kind of shows like a lag in the simulation where if you might have slower nodes. And so you still kind of see this growth, but even with this growth, it's nothing like the prior growth of the old simulations. And in fact, this growth is also encoded inside of the prior simulation with sampling nodes, but it's just kind of overshadowed by the fact that the rounds is growing so rapidly in that case anyways. So yeah, there's a good question internally on that, and so I wrote that up as a comment below, but wanted to shout it out as well. So yeah, fun stuff.
Yeah, always fun playing around with the consensus. Like, but there's nothing relies on that, so we should be good to change whatever.
I will say the actual lines of code changed is much more intimidating than the actual diff. Like, it's almost all changes in tests to just like provide these two different alpha values, compared to like the actual code is just like very similar to the change in the pseudocode, where it's just a couple of places that you just have to handle it slightly differently. But yeah, the diff of 1,000 lines doesn't do it justice. It's like a diff of like 100 lines, probably, maybe less. Anyways, that's my spiel.
Yeah,
in case you couldn't tell, the reason Steven is giving this spiel is that it still needs one more PR review.
Please review my PR.
Steven, would you say this one goes out to the whole community?
Yes. If anyone else approves it, I will be willing to merge it, regardless.
All right, you heard it here first, folks. So I mean, I think this goes into, just to kind of wrap up some of the stuff we've talked about, like goes into how we're thinking, at least at Avalabs, around like some of the platform development we're doing in AvalancheGo, which is, the layering of these abstractions and then independently optimizing these abstractions allows like a lot larger group of people to work collaboratively on like actually getting things done. And so, some of the core areas we're focused on are like consensus, networking, and storage. Last week, we talked a lot about some of the networking, or last session, we talked a lot about like pull request, gossip, and like the network P2P package. So that's squarely in the networking layer and available again for like any virtual machine to use on Avalanche. And right now it's on the C chain, but will be added to the X and the P chain, and maybe the HyperSDK at some point. The storage section, we have MerkleDB, ArchiveDB, Firewood DB, that are all working towards providing like efficient state management, or like agnostically across all sorts of different virtual machines. And then obviously underneath all of that underpins this, Avalanche style consensus, which, like anything in technology, is never in its final form. And so we're constantly experimenting with different ways to potentially improve performance, either, resilience, liveness, or reduce finality via different tweaks, changes to the actual mechanism itself. And then the hope there is that on top of that, it's become straightforward to build VM SDKs or VMs, and not really worry about all of these really cool things that are happening behind the scenes to unlock performance for the average person. And then connected via like warp and teleporter across all these things. So if you want the 30-second snippet of like where the focus is going, that's the focus. But I think it's cool to see like the evolution of all this stuff kind of start to intertwine itself more clearly and really get rolled out to actual usage, because we've been working on it for some time now. I think there's a few more things we can talk about. I'm trying to decide if we have time for that or if we should just preview it. Maybe the last what we should talk about real quick, because I think this was something that we didn't get to talk about last time, is the multi-dimensional fee create versus allocate discussion, which we had not yet discussed. So maybe, Steve, if you want to start off talking about a little bit what that is, and then I'll start pulling up the right slide for that.
Yeah, so as a bit of background here, we introduced multi-dimensional fees to the HyperSDK. So if you look at something like Ethereum, they have this thing called gas, and every opcode has a specific amount of gas that gets charged, and that's just kind of how pricing is done. For the HyperSDK, it becomes a little bit difficult to map everything to a single unit of gas because they're different resources. So as an example, you have maybe block space, which is kind of bandwidth. You have compute, which is very much just like CPU time. And then you have maybe disk IO and disk usage. So those are kind of three different resources that are tracked and are tracked separately. So if no one is using much compute, then compute becomes much cheaper to use. If no one's using bandwidth, then you can utilize more bandwidth. And you have this kind of more accurate pricing mechanism by separating these things out. But the one thing that is a little hard to track is the actual allocation of new state. The reason for that is because that is kind of allocated for forever. So whereas bandwidth, DBIO or CPU usage is kind of a current time cost that isn't recurring, creation of new state can, it just adds the value to the new state going forward until it gets deleted, if it gets deleted. So there's been a number of conversations around how best to price that, going all the way back. There's various talks in Ethereum about state rent, how do you want to do this? And so that we've been talking in depth about that. So Patrick, I don't know if you have something more specific that you want to go into with this, but.
Yes, I mean, the way that I think, funny enough, this actually came up when we were playing around with the HyperSDK GUI stuff. which is that Stephen made an observation that I started to push up the number of modifications that were happening per second on the network. So like, transfers between two accounts that already existed, such that when I sent like funds to a new account, such that like more storage was allocated, it was actually way cheaper to allocate storage like to a new address than it was to modify something that it was existing. And when we thought about that, we thought that was probably wrong, that the fee should be higher if that was the case. And the reason that's the way it is that we separate, and I'm trying to share the screen again, so sorry, I have it pulled up here. But the storage, we have separated, there we go, into create versus modification. And so when you create a new key, you're using the storage fee dimension. And when you modify a key, you're using the actual, modification dimension, right? And so if you have a bunch of modifications going on and then you create something, well, like they're separated, right? And the create dimension has no knowledge or influence by the modification dimension. And the reason for that, again, is like modification of state is a very different thing than creation or addition of state, and they should be priced separately. So the suggestion Stephen had, which I thought was pretty good, is to basically require all storage creations to also be a modification, and then to change storage creation more to storage allocation, which is basically you're setting a new key, but it has value 0, like you're creating a new key with value 0, and then you populate it via modification. So that means that no matter what is going on in the network, the cost of adding a new value into state is always going to be greater than, or strictly greater than the cost of modifying that key. Although the fee dimension is independent. I think there's more conversation to be had around exactly like you could actually floor like the create fee based on the modification. Like there's a lot of weird, tweaks we can have here. And for that reason, this whole package is like fully isolated out. So, we could add even more dimensions. Funny enough, I actually saw a different group who we had talked to actually at Stanford Blockchain Conference, creating a separate implementation of this that has a very different set of dimensions, which I thought was interesting. And so I'm curious to see like how we continue to research, in particular, like the usage of different fee dimensions to accurately price usage here. The other thing that we've talked about is also like the long-term cost of creation storage and like how to potentially price it such that as more state is allocated, not only is there like a iterative cost, but there's like some form of like pricing of allocation that you have to lock up to prevent like runaway storage usage when cost is low. So that's a whole nother conversation that I don't think we have time to get into, but I think this was a fun kind of innovation of what we're talking about here. And so, I have a bunch of stuff like this planned for like the 1.1 release of the HyperSDK. And right now, if you're curious where we're at, the DevNet one run command script is underway to deploy a full DevNet in a single basically script run that anyone will be able to do and then reproduce different sorts of load on. So that's really where our focus is now. But there's going to be a ton of different things that we have planned to change. And you can look at that in the milestone section, particularly for this V011. Tons of things here, which may sound really complex, but I know what I need to do. So we'll see how that goes. But cool. I think we're roughly at time here, so I think we can probably wrap things up. So maybe we'll go around. Any final thoughts?
Review my PR.
I was going to say review Steven's PR too, actually.
See, I've got a completely different view. People should just help us with Firewood. I think,
If you prefer Go, review Steven's PR. If you prefer Rust.
Sounds like there's PRs to review there, Ron. Yeah. Yeah. If you want to review any HyperSDK PRs, that's always an option as well. Yeah.
But on a more serious note, I'm really excited about kind of we're repicking up kind of some of the consensus stuff that we've been working on the theoretical side for a long time, and they're kind of getting pushed back into the implementation now. So I'm really excited about this kind of like renewed vigor that we have, and hoping that this isn't the last change to the consensus like this. But yeah, we'll keep pumping out those PRs. I'll try to keep up the description quality, but we'll see. Yeah.
Cool. All right. Well, thanks everybody. We'll wrap it up here.